We're going to talk about strong correlation. The interest primarily is strongly correlated materials. You know, there's a class of materials for which your standard density functionals works pretty good. And there's whole classes of materials for which it doesn't. And in particular, strongly correlated. Now, I'm not talking about superconductors. I'm talking about things like nickel oxide, where, or moderate correlation, people use PBE plus U, where you have to add a U in order to localize the orbital ground. Okay. So we'll talk a little bit about that, then how we learn exchange correlation from lots of data, and then this thing we created a couple of years ago, the Cohen-Sham regularizer, and then testing it on weakly correlated systems. Okay. So it turns out, in fact, I remember this, I was there at the time. This was the first attempt to use, let's say, modern machine learning for exchange correlation, 1996, right? That was way ahead of everything. That was in that original boom of neural nets that then fizzled because they didn't really have the computational power. But these guys very cleverly tried to get the exchange correlation potential using a neural network. Okay, so the problem, here's the basic problem. It's very well documented. This is H2. You pull it apart and you take, this is Hartree-Fock or B3-Lip, it doesn't matter, any density functional, and it'll dissociate to the wrong energies. Does not go to twice the energy of a hydrogen atom. It goes to something quite different. So this is when we stretch bonds, but these effects occur in solids, and they occur even more prominently. The more bonds you have, the more you break it, the more strongly correlated it becomes. And people have been studying this issue since about 1935, Coulson and Fisher, because it happens with Hartree-Fock, but it also happens with pretty much all your standard density functionals. And it's because the Cohen-Sham system, it has a single Slater determinant. Now, it's not really approximating the wave function, right? It's not supposed to be the exact wave function. But if you only have a single Slater determinant, it's very hard to make it associate to the two separate atoms, because the true interacting wave function is two Slater determinants, called the Heitler-London wave function. It's a 50-50 combination of two. The exact Cohen-Sham wave function is a Slater determinant, but somehow the functional knows how to get the right energy out. And a lot of the work, actually, this one is a little out of order, I think. Yeah, we'll get back to that one. The work I'm going to show toward the end was inspired by those guys. We'll get to that. So over the last 10 years or so, we developed this one-dimensional electronic structure lab where we do one-dimensional calculations, but they're designed to mimic real three-dimensional DFT. And this is all in collaboration with Steve White. And the reason we do that is because we can do density matrix renormalization group, pretty much the world's best numerical quantum solver, and it can handle any amount of strong correlation. So these are some of the graduate students we set it up with a few years ago. I'll show you, here's an example, which is missing a bunch of stuff, but I can tell you what it is, that's okay. So this is our one-dimensional H2 as a function of separation. This is the exact binding curve from MRG. One of these is LDA, maybe this one, and this one is Hartree-Fock, or it could be the other way around. And this is the, actually, I know this one is Hartree-Fock because it's going to the right level. So this little dot is called Coulson-Fisher point, where you break symmetry in your Hartree-Fock calculation, and then you can get it to go to the right energy, but the spin symmetry is messed up. And the same kind of thing happens with LDA. So this picture looks, it's qualitatively the same as the real three-dimensional case, but this is with a one-dimensional mimic. And the reason we do, there are two reasons to do it in one dimension. One is DMRG. Its efficiency and accuracy is fantastic in one dimension, and it starts going down as you go to 2 dimensions and 3 dimensions. And the other reason is if you want to get to the thermodynamic limit, the limit of an extended system, it's a lot easier in 1 dimension to go for an infinite chain than in 3 dimensions going for a cube. 100 atoms gets us to essentially infinity in 1 dimension. In 3 dimensions, that's 100 by 100 by 100. That's a million. That's way more expensive. Okay, so the first project of this kind that we did was actually, so this is a mistake that you may have noticed if you're a graduate student, that sometimes happens, where your professor asks you a question that's too hard. So I had a very good, really sort of brilliant physics graduate student, Li from China, and I accidentally asked him a too hard question, a sort of impossible one. So we had these methods for doing an orbital free DFT, and I said, let's do it for the real quantum system. But in order to do that, he has to sort of learn both the kinetic energy functional and the exchange correlation functional to, 1 kcal per limit per mole. And then we wanted to sort of, so that we would directly solve the DFT equations, the Euler equation, not even doing Cohen-Cham. But what we really should have done was Cohen-Cham and just learn the exchange correlation piece, much easier problem. Anyway, so one of the things, so he spent a year trying out all my suggestions and showing that they didn't work, all my ideas to get the density. So he couldn't learn the functional accurately enough so that you could differentiate it and get the density as well. And everything we tried, so we tried different representations of the density. And one time, he comes up with his own idea, he stops listening to me and solves the problem, which was great. So he used a basic trick, which I didn't have time to do yesterday, principal component analysis. And he used a trick from chemistry. So this was our illustration of principal component analysis. So one night I'm in a hotel room and I'm going to give the talk the next day at some meeting. And I had this idea of how to illustrate principal component analysis. So we do some facial recognition, right? So with my Apple machine, I take 16 photos of my face, and we're going to do principal component analysis on this, on my face. This is how some of the facial recognition works. But so he wanted me to have 16 different expressions on my face, right? But not only that, there's this, I can go into it, this business of centering and so forth, your data set. So he didn't have time to do that. So I had to make my face be in the same place in each picture, right? And apparently I did that well enough so that we could still do the analysis. He wasn't going to move it around. So these are my different face, 16 of them, right? So each of these pictures, right, I don't know, has, the order of 1,000 pixels. And we did it in black and white because he didn't have the computer resources to get it done by 8 a.m. the next morning. In black and white, so that's maybe 1,000 pixels. So that's a vector of 1,000, right? And what you do is you take the 16 pictures and you look at the directions in which there is the most variance. So the first you take the average of them all, and maybe this will work. We have this is what I call my mean face, my average face, right? And then one by one, you add in these principal components, right? And so you add in one principal component, and you might recognize me almost, right? I mean, you'd be a little frightened if somebody looked like that coming down the corridor, right? But once you added 7 components, that's pretty good, right? And so this one is actually this. I don't know which one.
Sodro.
Which one is it? I think it's this one. Right? He's reconstructing. I'm not sure. Anyhow, so with just 7 principal components, you can pull out all that data. So that's principal component analysis. So what did he do with it? So we had these chains of hydrogen atoms, and so this is the density in one of these chains, and he used a standard technique in chemistry called Hirschfelder partitioning, where you can resolve a molecular density into a sum of distorted atomic densities. Now this has got 8 atoms in the chain, and we did chains of different separations between the atoms. So then these 8 atomic things would look different in each chain. So he's going to decompose the full density into these guys. He centers them all. So these are all the atomic densities. I think there's about 800 of them in this picture. This red line is the average one. And he does a principal component analysis on all these densities. And then he's going to write, so here's the principal components, the first 7 or 8, first 7. And then he writes any of these atomic densities in the spaces set. But he only needs 7 coefficients to give each of these, so 56 numbers then characterizes the molecular density. So once he did this, and then he expresses our energy functional in terms of this basis set, and minimizes and so forth, it runs in a couple of minutes, instead of the days and days and days of all the real space stuff that I had suggested. So when he does that, the errors in our functional calculations go down by orders of magnitude, because we can run very fast, and we just sort of don't do very bad mistakes. And then, in fact, here's as a function of the number of training examples, this is the H infinity limit, and we're actually able to do periodic or infinite DMRG and show that our energies were good to chemical accuracy for the infinite chain limit. Now, I think I was talking to some of you. I think it was this one that was rejected by Physical Review X. They said that, because it was in one dimension, it wasn't important. So that ended up in Physical Review B. But I think if you check the number of citations here, it's a little bit higher than the impact factor of Physical Review X. Okay, so that was the first step of what Lee did for his PhD, and then he went off to work for a startup company doing cybersecurity. But then after a while, he wanted to come back to research, and so he ended up going to Google Accelerated Science. This is him here. And that's when we did this cone-sham regularizer work. This is Patrick Riley. This is Ekun Guguk Josh, who is now at Google Brain. And this is me and Ryan Pedersen. This was, I guess now it's over a year ago. But we worked on this for a long time, and we did the same thing on our one-dimensional system. But so now this is the one that's inspired by the Japanese work from Osamu Sugino's group. Ryo Akai is a graduate student who did really great work, and of course is now gone to a startup, which is a bit of an issue in this game. So what Ryo had done was he had taken three or four molecules and couple cluster calculations and trained not just the energy, but also on the densities of these molecules, made semi-local functionals, and then tested them on 150 molecules and showed that you could get answers as good or maybe a little bit better than the human designed functionals. And that really got me thinking, because I didn't realize you could use the density itself to train. So then I was chatting to Lee, and he thought about it, and he figured out how to do this. So in the work for his PhD, we would have a large amount of training data. What was surprising in Ryo's work was they only had three or four molecules total to train their function on. But they put the density in as a measure of how well into the cost function that we were talking about yesterday, and used it as a measure of the quality of the functional. So we determined to do that and see if we could also get results with much less training. And so this is in the sort of front page of the paper, and let me just sort of go through it a little bit. So this is using this scheme, and I'll explain what it is, called the cone-sham regularizer. And so these diamonds, so this is the H2 binding energy curve. These diamonds are the 2 points on the curve that we used for training. So one of them is picked near equilibrium, so that captures weakly correlated physics, and this one is when the bond is stretched, so that's going to have the strong correlation. And then there's one diamond here, which I objected to, but in the end he convinced me it was okay. It's called the validation point. And I think we only use the energy at the validation point. But it turns out to be important. And this picture down below is the error in the functional that the thing found. And this gray patch is this 1 kilocalorie per mole accuracy. So it's chemical accuracy that we're getting from just 2 data points. And we'll see that we can even do more than that. Do more systems than just H2 with this tiny amount of training. So this is called cone-sham regularizer global. It means it looks at the entire density. If we just did a local approximation or a GGA, you see the same usual errors where it goes up way too high. It has trouble. So it uses the same data, but goes bad. So this is the functional looking at the entire density. So how does this work? So what we do, in fact, is we train, you set the thing going with, say, no exchange correlation at all, and you do your cone-sham iterations, and at the end of each thing, you update your functional. Well, what's different is we train, we look at the loss, not just in the final converged cone-sham calculation, but in fact, as we go along in the cone-sham iterations. And we look back 15, I think, iterations, and we use the sort of how smooth the density is. In the previous iterations, we have a measure of the loss, both the energy and the density. And so what happens is, well, now it started off again. It keeps getting better and better. And in fact, it will overfit, of course, our one case if we don't put in a validation point. And that's called early stopping, and we have to stop it before. So this gives you, your usual 4 density function of the first time. I think this is the exchange correlation set to 0. But after that first set of iterations, it guesses a new functional and does it again. Let's see where it goes to. So this is a bit complicated. So this is a plot, basically a projection plot of the density. The density is complicated. We sort of just do it in a simple 2-dimensional space. And this is that first iteration, whereas the, is it here? Yes, this is the exact density on this 2D plot. But this region here is a region in which the error in the density is tiny. So all in that region there, it's tiny. So on that first iteration, we have a bad functional, and it sort of starts here and then wanders round. Then in the later iteration, you see that it comes down here, and now the density is looking almost perfect in that case. And you see it ends up in this regime where the density is very good, but if you keep on running it, it will overfit. It will make the density perfect for our one training point. So you don't want to go that far, and so as soon as it becomes acceptable, then you stop. And so the results, this is H2, so you can see, the error is too tiny to see. We did the same training for H4, just 2 points, and then we can get the entire binding energy curve, no problem with the strong correlation. H2 plus, we have a gate in the thing where basically it will force it to get 1 electron systems right, and so it does. And then this was one of the best results. We take 2 H2s and we keep them fixed at their regular bond lengths and vary their separation. And in these 1D cases, there is no van der Waals attraction. So the blue line here is what we got, and it's not quite chemical accuracy. But this is obviously a system that it was totally not trained on, right? There was no training data for these 2 H2s, and yet we still get really good accuracy. These things.
Kieron also couldn't quite understand the details. So LDA is not used to train the data. So you use the DMRG data, or
yes,
okay,
yes, it's all DMRG data.
Oh, I see.
And so this is the value of this 1D lab. Getting that kind of data for realistic systems can be very expensive. And then one last question we asked was, well, if it works this well for these strongly correlated systems, can you also use it the way Rio had done for weakly correlated, molecules at equilibrium? And it turned out, yes, it generalizes incredibly well, and this was Bucoli's contribution. And so in that case, in fact, we just trained on atomic densities, and I validated on one of them, and then tested on all these different molecules. And we didn't get quite chemical accuracy, but we got within a factor of 2, which is still much better than any human-designed density functional. These are densities that come out, and potential. The potential are not perfect, but they are very good in the region where there's a decent amount of density, which is what you'd expect. And yeah, and this is the, actually going back to the H2 binding curve that comes out from this, and now, so this is our weakly correlated functional, and it doesn't get you strong correlation. It behaves like a human design one, and if you break spin symmetry, then you do go to the right value. But for equilibrium properties, it's extremely good. It's better than what Rio's was doing. But ours are 1D examples, whereas Rio's doing it in 3D. Oh, one other innovation which I didn't mention is Rio. So there, I mentioned in the lecture yesterday about back propagation, and now all the codes really build this in, and you can then do sort of analytic differentiation. So for finding, the minimum of your cost function, once you have these analytic derivatives, you can apply all sorts of good methods for going downhill. Rio didn't have that, and so he would do Monte Carlo type steps on his cost function to find the minimum, which is unfortunately a very wasteful thing to do, because you take a step, you look, and maybe you throw out that step, right? So every time Rio wanted to rerun his calculation, it would take a lot of supercomputing power in Japan to find the minimum. But with this differentiable programming, all this happens very, very fast.
Then could you generalize this to the general three-dimensional case, this condition regularized idea?
In principle, yes. It's on our list of things to do, but if somebody else wants to.
But you need the exact data?
Yes, but the first thing to do would be just do these sort of hydrogen type chains again. That's not so hard. But you need quantum chemical methods, not DFT methods, right? You got to try to go beyond DFT. So.
Data is exact density, is that right? Data is exact density.
It includes the exact density, which is not so common, it turns out, to pull out from a CCSD calculation, because it's not something you need to do a CCSD calculation. So coupled cluster methods are not they're not variational anyway. So there's in fact 2 or 3 different expressions for the density that you can extract from a coupled cluster calculation, and they all have slightly different answers. And most codes don't give you the density. So it's a little non-trivial in that sense. Okay, and these are just pictures of our stretched H2 and how much features of the exact exchange correlation potential you get by lithium hydride. Okay, this was made a big blast. This is the DM21 functional. So this came out a little over a year ago, and a bunch of people, James Kirkpatrick was the main guy, but there are a couple of known sort of DFT people on this collaboration, and they took a slightly obscure form of approximate functional, a range-separated local hybrid. And this hadn't been explored much in DFT literature because it's complicated to think about and hard to get it to work. But they created some very large data sets, and got it to work by a fairly massive amount of training. And in particular, that seemed to be able to break bonds correctly, at least some of them. And so, yeah, so here we have pictures of correct bond breaking with a few tricks. So a lot of people sort of discussed this at the time. And in fact, there's a very nice magazine, Quanta magazine, put out by the Simons Institute, and spent a lot of time chatting with the reporter, and we don't actually know what what's actually going on in that picture. Have I done it again? No. Okay. Yeah, here we are. This is some nice picture of orbitals doing something or another, but he gives a very nice discussion of what this functional is and what it means. Now, since it came out, a lot of people have tried to use it, and if you look at the citations, there aren't that many citations to it. One of the issues is that it can be very expensive to create, to run, but also its convergence is very questionable. And even in the paper itself, in the supplemental info, they list cases where they couldn't get it to converge, which is a bit of an issue if you're doing anything high throughput, right? So there are issues with this functional. It hasn't taken off the way I would have expected it to. And then we discuss it in commentary thing for intro reviews. Okay. And then this was the last thing that so Lee worked for Google Accelerated Science, but then went on to better things. The better thing in that case was YouTube Shorts. He said, having spent 5 years of his life trying to improve humanity's lot, he would spend the next few years trying to get people to waste millions of hours watching YouTube Shorts. Well, what he and Patrick did, and a few others, were this searching for symbolic density functionals. So, simple formulas, searching through all possible simple formulas to make density functionals. So these look like the human designed functionals. And they wrote this nice paper. He was his intern just before, or actually just after, I think they both left Google Accelerated Science. Now the functional that they find is only about as good as the usual human design functionals. Doing symbolic regression is a very hard problem. That's a big problem in machine learning. And it's very hard to search over simple formulas and things. But anyway, they got it working well enough. And what's nice is what pops out are things that look like a person had designed the functionals. Okay, to summarize, so we can use machine learning to find the exchange correlation functional. But in that case, the stuff that Lee did for his PhD, you need data and feature engineering to get it right. With this cone-sham regularizer, so you're looking at both energy errors and density losses, and you need the full differential programming. It's too expensive to optimize otherwise. But it's a very efficient way to get chemical accuracy with very little data. And then what we saw is that it also works for the original problem that Rio was working on to get a good functional for weakly correlated systems. Again, Rio's work was with approximate functionals like GGAs and things. we were trying to get, a thing that generally depended on the density, we could get higher accuracy. But a problem with all this work is, again, I said the same for the orbital free DFT. In some sense, it's too good. It is actually finding the unknown density function. It looks at the entire density and uses that to figure out the energy. Now, the Holmberg-Kohn theorem tells you that that is possible, and this is a practical implementation of exactly that. But again, as I sort of emphasized before, it turns out that isn't really what you want. Be careful what you wish for, because that functional dependence will change every time you switch one atom out for another. If you think about it, that's kind of, there are limited contexts where this is useful, but it isn't useful like DFT is useful, where you can apply it to everything and every combination of elements, right? I'm not saying it's accurate, but it gives you results for that. Again, we have to go back and do some feature engineering to find find descriptors that condense all the information of all this density and still give this kind of accuracy. Now, you could either do that the old-fashioned way. Your physical intuition tells you this is an important quantity, that's an important quantity. Make a list of them all and try them out. Or we can take the functional we already have and use things like auto-encoders to compress the information and then re-expand it and see if we don't lose accuracy, then we're reducing how much info we need. But in a certain sense, it's like we have to go back to an atom-based system, right? Something which uses the chemistry of the system in order to find the function. And with that, I'm stopping. Thank you.